Why do you not fall through your chair right now? It seems like a child's riddle, but it is the perfect doorway into the deep order of the world. Your body leans into the seat pushes back, and you stay put. That quiet balance is not an accident. Three of nature's great forces are at work in that ordinary moment. Gravity is pulling you downward. Electromagnetism stiffens the atoms in the chair and the atoms in your skin, so they resist being squeezed into the same space. Deep inside every atom, another force keeps the atomic heart from flying apart. You do not notice any of this. You simply sit. But in the background, a grand orchestra plays. And lately, some careful listeners think they hear a faint extra note that does not fit the score we thought was complete. Let us meet the players one by one, starting with the most familiar giant of them all. Gravity is gentle and patient. It does not spark or flash. It simply pulls. It keeps you on the ground, the moon in its path around Earth, and Earth in its path around the sun. It is strangely weak when you compare it to the other forces, so weak that a small fridge magnet can lift a paper clip against the pull of the whole planet. Yet gravity never stops and never runs out with distance. Its reach is endless. People often picture it the way a heavy bowling ball bends a stretched sheet. That picture is not exact, but it gives the right feeling. Massive things bend space and time, and other things follow those curves. We have tested this idea again and again, from the way light bends around the sun to the tiny differences in time measured by clocks on Earth and in space. The tests keep agreeing with the theory. Still, scientists keep checking for tiny cracks, because even small changes in how gravity fades with distance could hint at new physics beyond what we know. If gravity is the quiet giant, electromagnetism is the everyday magician. It makes light. It carries radio waves. It is the invisible web inside smartphones and power lines. It is also the reason you do not sink into your chair. The atoms in your body and the atoms in the chair push back on each other because the charged parts of atoms do not like to be crowded into the same place. The same force holds atoms together in molecules and makes magnets cling to a fridge door. Turn a coil of wire near a magnet and you get a motor. Run a changing electric field through space and you get a wave of light. More than a century ago, James Clerk Maxwell wrote the simple set of ideas that ties all this together. Those ideas still guide engineers and scientists today and sit at the core of modern life. Now zoom down to the center of the atom, where the strong nuclear force rules. It is the atomic glue. Protons and neutrons huddle together in the nucleus, even though protons carry the same kind of electric charge and should push each other apart. The strong force overpowers that push at extremely short range and binds the nucleus tight. It is the mightiest of the four forces, but it does not reach far. Outside the nucleus, its grip fades almost to nothing. Without this glue, every atom would fall to pieces, and with it, the world is possible. Our best understanding of the strong force lives inside a theory called quantum chromodynamics, which has been tested in countless ways and folded into the larger framework that describes the other known forces of particles. The weak nuclear force is not weak in the sense of powerless. It is the cosmic recycler. It allows certain particles to change identity. It turns a neutron into a proton and an electron and a ghostly neutrino. That quiet swap is what we call beta decay. In the heart of the sun, chains of such weak interactions help turn hydrogen into helium and release the light that warms Earth. The weak force is also built into the grand particle framework that has guided physics for decades. It is the reason some elements are unstable and the reason detectors on Earth can catch whispers from the sun and from distant nuclear processes in the sky. When we step back, we see why for so long these four forces seem to cover everything. Three of them, the electromagnetic, strong and weak, are wrapped into what physicists call the Standard Model. It is a precise, hard-won structure that predicts how particles should behave and how forces should act among them. It has been checked in deep detail at colliders, in underground labs, and in tabletop experiments. Gravity is not part of that same mathematical package, yet general relativity, our best description of gravity, has also passed every test so far. Together, these ideas explain almost all we see, from the spark in a neon sign to the arc of a galaxy. This is why many physicists speak of the Standard Model as one of the greatest achievements of human thought. It is not just a list of facts. It is a tight and beautiful web of ideas that keeps making right prediction to many decimal places. One of the cleanest ways to test the full web is to study a short-lived particle called the muon. Think of it as a heavier cousin of the electron. When muons fly through a magnetic field, their internal compass wobbles in a way that can be calculated with great care using the known forces. The measurement, it is hard, but possible, and any mismatch between the wobble we predict and the wobble we see could signal something new, nudging the muon. A series of experiments in the United States has been chasing this number for years. In a major result, the team at Fermilab reported a very precise measurement of the muon wobble that sharpened the long-standing tension between experiment and the theory value many groups had accepted. That tension set off a new round of intense work to refine the theory side, especially the part that depends on the strong force. Because the strong force is tricky at low energies, different methods can give slightly different answers. In recent peer-reviewed studies, a powerful method called lattice quantum chromodynamics has shifted the theory estimate in a way that eases the tension. The story is still unfolding, but this is how science moves forward. We measure, we compare, we argue, and we improve both the data and the theory until the truth becomes clear. Hints of something new have also been hunted far from laboratories, out in the quiet paths of small bodies that wander the solar system. When spacecraft track the motion of asteroids with radar and laser light, they can forecast their paths years ahead. Now and then, tiny drifts show up that do not match a first simple gravity-only model. One well-known cause is sunlight itself. When a darker boulder warms in daylight and cools at night, it gives off a tiny push that can slowly shift its orbit. This subtle effect, called the Yarkovsky effect, has been measured for the asteroid Bennu and is now part of the standard way we predict its motion. It is not a new force of nature, just the old ones, acting in a small but steady way. Even so, the hunt for such small tugs has sharpened our tools and has kept open the question of whether any unexplained tug remains once all known pushes and pulls are counted. There have been other puzzles in spaceflight. Years ago, several spacecraft appeared to gain or lose a tiny bit of energy during close swings around Earth. The effect was nicknamed the flyby anomaly. It sparked lively debate and many checks. Before that, two distant probes called Pioneer seemed to slow down more than expected as they drifted into the outer solar system. After careful detective work, the Pioneer case was traced to the faint push of heat radiating from the crafts themselves. This result showed how a mystery can vanish when a mundane source is properly measured. The flyby case led to more careful modeling of Earth's environment and spacecraft motion. The lesson from both stories is steady and humble. When the numbers do not add up, we first tighten our models of known physics, and only if a gap remains do we begin to suspect a new law. So why did the four Guardians feel complete for so long? Because time and again, they passed every test we could throw at them. Because particle colliders confirmed their rules, and space missions found their fingerprints where we expected them. Because the equations that describe them were not just clever, but predictive. In the standard model, the electromagnetic, weak and strong forces merge into a unified language that has predicted new particles before we ever saw them. And then those particles showed up right where the theory said they would. In gravity, the curves of space and time have explained the motion of stars, the swing of a pendulum, and the ripples of gravitational waves from colliding black holes. In each case, the numbers have matched the world with astonishing accuracy. And yet, the best part of science is that it is never entirely satisfied. A careful experiment that whispers something off-key is not a problem. It is an invitation. The muon wobble story is one such whisper. The delicate drifts of small bodies in space, once we subtract sunlight and outgassing and every known source of push or pull, are another place where a new whisper could hide. Many teams now look for such whispers with fresh patience and better tools. For the muon, new runs have raised the precision of the measurement, while independent theory groups keep narrowing the uncertainty in the calculation, so that if a difference remains, we will know it is real. For asteroids, sample return missions and long tracking campaigns are giving us sharper pictures of size, spin, and surface, so the small thermal pushes can be computed and removed with care. What if, After all this careful work, a true gap remains. Then we face a thrilling question. Could there be a fifth force, a very shy partner to the four we know, that shows itself only in the finest details? If so, it would not erase the old forces. It would sit beside them, perhaps weak and short-ranged, perhaps tied to dark matter, perhaps visible only under special conditions. This is not a claim, but a possibility. The way to tell is the way science always tells. Repeat the measurement, change the method, ask another lab to check. If the signal stands through all that, then the textbooks will need a new page. If it fades, we will have learned something precious anyway, because we will know more about how the known forces shape the world. That is the heart of this book. We will keep sitting in chairs, watching phones light our faces, and listening for the faint extra note that might change the song of reality. When a careful number does not match the number we expect, the first feeling is not panic, but a tension. A quiet mismatch is how science often finds its way to something new. The story begins simply. A measurement is made again and again until the people who did it can say with confidence what the world did in that one small experiment. Then others try to do the same thing in a different place with a different tool. If the numbers agree, we breathe a little easier. If they do not agree, the laboratory becomes a kind of detective room, and the discrepancy becomes a clue. The history of physics is full of such clues. Tiny slips in a table of numbers have led to new particles, new laws, and whole new pictures of how the world is built. Precision is the flashlight in that dark room, and careful repetition is the hand that checks the lock. The muon is a good example of this detective work in action. Imagine an electron that wears a heavier coat. It looks like an electron has the same electric charge and the same spin, but it is about 200 times heavier, and it only lives a tiny fraction of a second. Because it is heavy and simple, the muon is very useful as a probe. Physicists push beams of muons into a precise magnetic field and watch how the tiny internal compass of each muon wobbles as it spins. The size of that wobble is something we can calculate from the known forces and particles. If the wobble seen in the lab is different from the wobble the theory predicts, then something small and new might be tugging on the muon. That is why experiments at Brookhaven and later at Fermilab set out to measure the muon wobble with extreme care. The Fermilab effort first published a striking result, showing a tension with the expected value, and that tension has been the subject of intense study ever since. The experimenters have now released a final high-precision measurement that reinforces their earlier findings, while at the same time, theorists work to sharpen the calculation that the experiment is being compared to. Part of this debate turns on how the strong force dresses the vacuum and how that effect is calculated using ordinary data or by heavy computer simulations known as lattice QCD. Different approaches have pushed and pulled the theoretical number, and that is why the muon story still reads like the first chapters of a long mystery. Not all odd numbers come from inside particle labs. Some arrive from the sky, When spacecraft track a small rock for years, they can predict where it will be within meters, decades into the future. That careful bookkeeping lets us test gravity and other forces on new scales. The asteroid called Bennu has been watched up close by the OSIRIS-REx mission and from ground telescopes. The data are sharp enough that physicists can now ask whether the tiny pushes that we understand are enough to explain Bennu's motion, or whether an extra whisper of force might be needed. Often the extra push turns out to be ordinary physics, pushed to small scales. For example, heat from sunlight, warming the surface, and then re-radiating away can give a steady, tiny shove that changes an asteroid's orbit over years. That effect, called the Yarkovsky effect, is small, but predictable. And once it is accounted for, the motion of Bennu becomes far less mysterious. Still, with the OSIRIS-REx data, scientists were able to use Bennu as a testbed to set new limits on hypothetical new forces, showing how space missions can act as quiet laboratories for fundamental physics. At the same time, history warns patience. Earlier spacecraft oddities, like the Pioneer anomaly, once suggested new laws, but careful accounting of heat and other engineering details explained them with known physics. The lesson is gentle. An anomaly is a whisper that deserves listening and careful cross-checking, not a shout that demands a new theory before every other possibility is checked. In ordinary laboratories on Earth, there is a growing set of experiments that look for forces we did not expect. Some of these use big machines, like particle colliders, and some use very small, precise tools, like atomic clocks, lasers, and torsion balancers. The torsion balance has long been a quiet hero in this search. It can test whether gravity behaves as an inverse square, or whether a tiny new force pulls differently on different kinds of matter. The groups that run these experiments have steadily pushed the limits, and in the process have closed off many simple ideas for a new long-range force. In another corner of the precision world, atomic and optical methods have become powerful detectors of new interactions. By comparing the tiny frequency differences in atoms of different isotopes, physicists can look for a force that would tug on neutrons differently from electrons. Recent isotope shift and King plotter studies have reached sensitivities that probe new bosons in mass ranges that were hard to reach before. Those tabletop detectives are slow, careful, and increasingly clever at squeezing new physics out of what, at first glance, seem like routine measurements. The pattern that emerges is a mixed one. There are isolated anomalies in different places that do not all point to the same solution. Some very persistent claims come from dark matter searches. One long-standing example is the annual modulation signal reported by the Dharma experimental program, which observes a seasonal wobble in event rates that its team has argued matches what would be expected from dark matter in our galaxy. Other experiments with different materials and methods have not reproduced that signal, and so the community treats the claim with care and invites independent checks. Another story comes from the Xenon 1T detector, which in a run a few years ago saw an unexpected excess of low-energy electron recoil events. That excess lit up a flood of papers suggesting explanations from mundane to exotic, and spurred follow-up runs with newer detectors. Sometimes an excess fades as the next experiment tightens the net. Sometimes it leads to a new particle hypothesis that survives many checks. The wider lesson is the same. Anomalies must pass the tests of repetition, independent confirmation, and a firm link between cause and effect before they flip from curiosity to new law. Particle colliders add another thread to the tapestry. In the decays of heavy mesons, some measurements have seemed to disagree with the standard expectations for how electrons and muons should appear in the final states. These so-called flavor anomalies are subtle and spread across many decay channels and experiments. Some measurements have moved closer to the standard model as more data arrived, while others have kept their tension. Physicists watch these signs like a trail of footprints. They are difficult to interpret on their own, but if many trails point the same way, then a map begins to form. Right now, the map is still tentative, and the search is active. All of these pieces together make a detective story without a final chapter yet. Tiny mismatches in the muon wobble the careful tracking of an asteroid, the faint scatterings deep underground, and the minuscule shifts in an atomic clock all add to a growing list of questions. Each case is different. Each needs its own follow-up. Sometimes an apparent mystery dissolves when an instrument effect or a missed background is found. Sometimes the mismatch persists through many careful cross-checks, and then something new must be invented. The patient, steady work of checking and rechecking is not glamorous, but it is how breakthroughs happen. Scientists do not rush to headlines. They repeat, they vary conditions, they build new tools, and they invite others to try the same thing. In that slow method, there is a strange beauty. The world yields its secrets one careful number at a time. If a fifth force exists, it will not arrive with trumpets. It will probably show itself first as the same sort of small, stubborn discrepancy we have seen again and again. The job right now is not to declare a new law, but to keep the lights on the clues alive and to follow them wherever they lead. The more precise the measurement, the clearer the path. The more independent the checks, the firmer the ground. That quiet, patient detective work is the best chance we have of finding whether the known forces are truly the whole story or just the main characters in a play that has one or two other actors waiting in the wings. There is a moment in scientific work that feels a little like stepping into a quiet attic with a flashlight. The air is still. Old things sit where they have always sat. Then the light catches something odd in the corner, a small object that does not belong. That is what the hunt for a new force feels like to the people who do it. It begins with a number that will not quite fit the chart, with a track in the sky that drifts a fraction off from prediction, with an instrument that hums a note different from the rest. Those tiny mismatches are invitations. They ask us to look harder and to build better tools so that the truth can be separated from mistake or misread data. One set of tools lives at the edges of our reach and is built to make the very small very visible. Particle accelerators are giant microscopes. They push bits of matter to very high speed and smash them together so that for a sliver of a second, new particles and new forces may appear in the debris. Machines like the Large Hadron Collider are not only powerful, and noisy engineering marvels, they are also extremely careful recorders. The teams that run them examine billions of collision records, looking for patterns that do not belong to the familiar cast of particles. Over the last years, the Collider experiments have searched for signs of new force carriers, such as dark photons or heavy Z prime particles, and they have turned up important limits that guide theory and future searches. That steady negative result is itself a kind of map telling us where a new force is not hiding and where it might still be found. Other tools take a very different tack. Instead of building stronger collisions, we make quieter and more precise clocks and balances. Atomic clocks measure time so precisely that tiny shifts in energy levels inside atoms can be detected. Those shifts can reveal whether an extra weak force is tugging differently on neutrons and electrons. Laser interferometers measure distances so cleanly that a whisper of extra motion can be seen. Sensitive magnetometers and torsion pendulums can test whether the pull between two small masses follows the Newtonian inverse square law or departs from it in ways a new force would predict. For decades, one of the most patient groups in the field used a torsion balance to set extremely tight limits on forces weaker than gravity and on whether different materials fall in the same way. That work has narrowed the options for a long-range new force and pushed researchers to look instead at weaker or shorter ranged possibilities. Space gives us a third kind of laboratory. A small rock that drifts through the solar system follows a path written mainly by gravity and the light of the sun. But when we track that rock with lasers, radar, and precise spacecraft navigation, we can test whether those known pushes fully explain the motion. The OSIRIS-REx mission that visited the asteroid called Bennu gave us unusually sharp data. Scientists used that data to test and to place limits on a hypothetical extra force that would change the asteroid orbit in a way that gravity and known thermal pushes do not. In the same way that the Pioneer story taught us humility about unexplained spacecraft quirks, the Bennu work teaches care and sets useful bounds on how strong a new force could be in the space around us. A very modern thread in the hunt is the use of isotope shifts and the King plot technique. When one measures the light absorbed or emitted by different isotopes of the same element, tiny differences appear. Those differences mostly come from well-understood nuclear and electron effects. If a new force that couples to neutrons existed, it would add a small extra term to the pattern of shifts. By making ultra-precise measurements in atoms, like calcium, ytterbium, and strontium, researchers can spot or rule out such an extra term. In the last few years, teams have pushed these measurements into precision that can constrain new light bosons over ranges that were once unreachable. This approach lives on tabletops and yet reaches into questions usually addressed by the largest machines. Behind every signal hunt, there is a statistical story. Data arrive messy. Detectors have quirks, and backgrounds can impersonate signals. Physicists use careful statistical rules to sort chance from real effect. A rough rule of thumb in particle physics has been that a finding must be very unlikely to be a fluke before it is called a discovery. That is why multiple independent checks matter and why the community scrambles to reproduce and cross-check. The tools of modern statistics used in particle searches let scientists combine different measurements, include systematic uncertainties, and test how robust a hint is against different assumptions. That patient, statistical detective work is what separates curiosity from claim. The hunt for a fifth force is therefore both local and global. Local in the sense that small teams with precise clocks or balanced pendulums can reach very deep, and global because large collaborations share dataset standards and methods across continents. Teams working at accelerators share their data with theorists who propose new models and with other experimental groups who try different approaches. Missions in space coordinate with ground-based observatories and lab experiments to cross-check strange results. This web of cooperation makes the search stronger because an oddity that appears in only one place can be tested in another way somewhere else. The culture of modern physics is both competitive and cooperative, and that tension helps the field avoid mistakes while keeping the pace of discovery alive. Right now, many experiments are still looking, and many recent results have tightened the net. The muon anomalous magnetic moment remains a headline case because it is a very precise number that is hard to calculate and hard to measure, and because it is sensitive to many possible new ideas. Space-based tracking of asteroids has turned some earlier puzzles into firm limits. New tabletop atomic and isotope shift studies have set fresh bounds on light bosons. Collider experiments have closed off large ranges for heavy force carriers. Each null result is not a failure, but a narrowing of the map. Those narrowed maps tell theorists where to point and give experimentalists new niches to explore. Imagine a room full of very bright people sitting quietly and thinking in the same way a painter sits with a blank canvas. They imagine things that cannot be seen, and then find ways to check whether those imagined things might be real. This is how theoretical physicists work. They dream up simple ideas that could explain odd measurements, and then the experimental teams build clever tools to test those ideas. Dreaming in physics is not fanciful wishful thinking. It is careful play with equations that later must meet the stubborn court of experiment. The idea of a fifth force grew from that kind of careful play because small mismatches kept showing up in numbers that otherwise fit the known rules. One of the clearest bridges between wild ideas and experiments is the way theorists think about dark matter. The visible stars and gas in galaxies do not add up to the motions we see. Something invisible seems to hold galaxies together. This invisible part might be particles that barely talk to ordinary matter, or it might be something more subtle, like a new force that only the invisible stuff feels, and that pushes or pulls in its own way. If dark matter carries its own force, it could tug on ordinary atoms in small ways, or it could change how dark clumps form over time. Searching for that kind of communication between the dark and the bright is a very active area of study and connects particle physics to astronomy and cosmology. Other thinkers ask whether gravity itself hides a secret. In some ideas, gravity looks right at the distances we know, but behaves differently at very small or very large scales. Extra dimensions, for example, could let gravity leak away from our familiar space and make it seem weaker than other forces at short range. Those ideas seem wild because they bring more dimensions than the three we walk through, but mathematically they can be tidy and in some version as they solve serious puzzles about why forces have the strength they do. Physicists test these ideas by pushing precise experiments to tiny distances and by watching how stars and galaxies move with great care. A lot of the math is heavy and the predictions subtle, yet the experiments are getting strong enough to rule out many simple versions of these ideas, even as they leave room for more subtle possibilities. Some proposals sound like science fiction, but are really sensible extensions of what we already use to explain things. For example, a new particle that carries a force can be light or heavy. It might only affect spinning particles, or it might only work over a certain short length. If the new particle is light, it can mediate a long, weak push that shows up in the motion of celestial bodies or in tiny, strange shifts of atomic energy levels. If it is heavy, the effect is short-lived and only appears in high-energy collisions. These differences matter because they tell experimenters what tools to use. A beam collider will hunt for heavy carriers, while a tabletop clock or an atomic spectroscopy lab may be the right place to find a light-shy force. Among the clever proposals is the idea of a field that hides itself depending on the local environment. A chameleon-like field can act strongly in empty space, but become almost invisible inside dense places like the Earth. That property lets it pass the many tests we have made on the ground while still having a role in cosmic settings. The chameleon picture came from the desire to have a field that could explain cosmic acceleration or other cosmic oddities without upsetting the carefully checked laboratory physics. It is the kind of idea that shows how imagination and restraint go together in theoretical work, because the theory must hide itself where we have already looked closely while revealing effects where we have not looked as carefully. Other familiar names come into the story as natural candidates for force carriers. Axions. An axion, like particles, began life as a neat solution to a problem inside the strong force of particle physics, but they also make excellent dark matter candidates, and they can mediate new kinds of interactions. Axion, like particles, tend to be light and weakly coupled, and that is exactly why they are hard to find. Yet many clever detectors now search for their faint signs in cooled, resonant cavities in underground labs and with astrophysical observations. The long list of possible particles that theorists propose builds a kind of menu of searches, and each experiment checks one item on that menu so that over time the menu gets smaller or more focused. All these ideas lead to many kinds of experiments and many ways to be fooled by ordinary things. Theorists, therefore, try to make ideas that give clean signatures, something that cannot be mimicked by heat leaks, or tiny magnetic impurities, or by the way light warms a surface and gives a faint push. Theorists also try to find simple models that give clear predictions, because then experimentalists can make a single sharp test and either rule the model out or give it new life. That back and forth is the core of the modern process. Theory imagines plausible new actors, and experimenters build tests that are as direct and clean as they can be. A sober but exciting point is that this harvest of ideas from theory does not all point in one direction. Some anomalies can be explained by subtle conventional effects, while others remain stubborn. A good example is how asteroid tracking has become a laboratory for testing ultralight fields. If a new very light force existed, it could slightly change the precession of an asteroid orbit over years. Modern observations, including close-up spacecraft data, can place strong limits on how large such effects could be, so that some classes of fifth force models are already tightly constrained. space missions, and ground-based telescopes together make the cosmos into a patient detector for the faintest of tugs. In the end, the theories are a kind of invitation. They promise new pictures of the world if measured evidence supports them, and they require humility when the evidence does not. The wild ideas are not fantasy. They are careful mathematical possibilities that must answer many practical questions before they survive. The chase for a fifth fundamental force is therefore not a rush to declare a revolution. It is a long, gentle conversation between bold imagination and stubborn experiment. The reward, if found, would be immense. A new line in the ledger of nature and a new way to see how the universe holds together. Until then, each new idea is a bright question mark that guides where instruments point and where observers look in the sky and in the lab. The experimental search for a possible fifth fundamental force feels like a long, gentle race where every step is measured in fractions and every breath is checked twice. Scientists work in different labs and in different ways, but they share a common aim. They want to find anything that nudges a particle or a small body in a way that the four known forces cannot explain. That hunt is competitive because groups want to be the first to find something new. But it is also deeply collaborative because a true discovery must survive tests from many places. The pressure to be first pushes teams to build bold instruments and clever analyses, and the need to be right keeps them honest through repeated checks and open data sharing. The whole field moves forward by careful comparison of numbers rather than by bold claims alone. One of the most watched campaigns has been the long-running muon G-2 project. The muon is like a heavier cousin of the electron, and it is a simple, clean probe of how forces act at very small scales. The experiment stops muons inside a massive magnetic storage ring and watches how their tiny internal magnets wobble. Small shifts in that wobble can mean that unfamiliar particles or forces are tugging on the muon. For many years, the measurements and the theoretical calculations did not line up perfectly, and that mismatch was a headline, making lead into the idea that new physics might be at work. The Fermilab team completed its data runs and released a final, extremely precise measurement in 2025, which sets a new experimental benchmark. That measurement tightens the rules and gives theorists a clear number to match. The muon story also shows how subtle the interplay between experiment and theory can be. On the theoretical side, the hardest piece to compute is how quarks and gluons produce a hadronic vacuum polarization effect that slightly shifts the muon wobble. In recent years, powerful lattice QCD calculations have produced numbers that move the theoretical prediction closer to the experimental value. Some of those lattice results come from large international collaborations and are published in highly regarded journals. That progress in theory is why the current conversation is not simply about whether the muon proves new physics, but about how reliably we can calculate every contribution to the standard expectation. In short, the muon test is a high-precision mirror, and both sides of that mirror have to be polished. Not all experiments live in giant rings and underground caverns. Space missions and tiny tabletop devices also take part in the hunt. The OSIRIS-REx mission that visited the asteroid Bennu gave scientists a close-up view of a small world being pushed by sunlight and tiny thermal effects. Measuring how Bennu drifts lets researchers ask whether ordinary effects, like heat, recoil, fully explain its motion, or whether a faint extra pull is needed. So far, careful accounting of thermal forces explains much of the observed motion, but the precise tracking of asteroids has become a new way to place limits on any long-range, weak force that might act differently in vacuum than on Earth. Space is a clean place to look, and missions like OSIRIS-REx show how planetary science and fundamental physics can work hand in hand. Deep underground detectors and dark matter experiments form another part of the experimental battlefield. Teams build huge tanks of ultra-pure liquid xenon and other materials and wait patiently for the faintest interaction a dark particle or a new force might leave behind. Experiments such as LZ and Xenon T have pushed sensitivity to unprecedented levels and keep reporting that they do not see the signals that many simple theories predicted. Those null results are not failures. They are powerful guides that rule out broad classes of models and narrow the space where a new force might hide. The quiet, patient work in these labs shows how eliminating possibilities is just as important as finding surprises. Tabletop experiments are often the unsung heroes in this search. Precision atomic clocks, torsion pendulums, and magnetometers can detect minuscule forces that giants cannot. The torsion balance is a classic instrument which measures whether different materials fall in the same way and whether gravity follows its inverse square rule at tiny distances. Atomic spectroscopy methods compare light absorbed by different isotopes to look for tiny extra shifts that a new boson could cause. Recent work using isotope shifts and King plot techniques has reached levels of accuracy that begin to constrain hypothetical light force carriers. These small-scale approaches are inexpensive compared with multi-billion-dollar colliders, and they can probe mass ranges and couplings that large machines cannot. All of these searches face the same patient logic. An unexpected blip prompts questions. Is the instrument behaving exactly as we think? Does the background look different? Under another analysis, can some mundane physical effect mimic the signal? If the answer to those checks is yes, the anomaly fades. If the answer remains no, after independent groups try different methods, then the anomaly grows in importance. Modern science sets a very high bar for claiming a new fundamental force, because the consequences would be so large. That bar includes multiple independent confirmations, detailed accounting of systematic errors, and careful cross-checks against theory. The narrative is, therefore, slow and steady, rather than dramatic. Each null result that arrives after a tight search is itself a useful piece of knowledge that prunes the forest of theories. Competition between groups also spurs innovation. Labs push detectors to lower noise and finer control. The need to beat limits encourages new ideas in laser cooling, clock stability, superconducting sensors, and data analysis. At the same time, the community shares data and methods openly so that claims can be tested and reproduced. International collaborations bind together accelerator teams, instrument builders, astronomers, and tabletop experimentalists. The result is a healthy tension of rivalry and collaboration that helps science avoid the temptation of premature announcements while keeping the pace of discovery alive. Finally, there is the place of negative results in the story. When a careful experiment finds nothing, it does not kill curiosity. It sharpens questions and redirects searches. A null result can close large swaths of theory space and tell theorists where to look next. The current state of play is a long list of well-checked limits, a few persistent anomalies that still need independent confirmation, and a lot of new ideas being born and tested. The experimental battlefield is quiet and rigorous, and that steadiness is exactly how revolutions begin. If a fifth force is waiting to be found, it will almost certainly appear first as a careful, stubborn discrepancy that survives years of checks and then blooms into a new picture of nature. Until that day, experiments will continue to push the limits and to make the invisible visible through patience, precision, and collaboration. There is a quiet, human story at the heart of every great scientific leap. The story begins with a number that will not behave, with a chart that will not line up, with a machine that sings a note in the wrong key. At first, the reaction is practical. Check the cables, check the code, check the calibration. Only after every ordinary cause is ruled out does the whisper become a question worth shouting about. This pattern of caution followed by curiosity has shaped the history of physics and kept it honest and strong. One clear chapter in this history came in the mid-1980s, when a group of researchers re-examined old measurements that dated back to the early 20th century and suggested that gravity might carry a small extra twist. That claim grew quickly into what people called the fifth force controversy. For a while, many teams around the world tried to repeat or refute the signal. Some experiments seemed to show hints, others showed nothing. And over several years, the balance of evidence moved away from the original claim. The episode is valuable not because it produced a new law, but because it showed how the scientific system corrects itself through repetition, discussion, and careful checks. The controversy prompted new experiments that improved methods and tightened limits on how any new long-range force could behave. Another useful case shows how a mystery can fade under patient investigation. Two deep space probes called Pioneer 10 and Pioneer 11 seem to drift slightly off the paths engineers predicted. For years, people wondered if the probes carried a message from new physics. The eventual answer was much more ordinary, and in that ordinariness, a lesson was hiding. Careful thermal modeling showed that heat escaping unevenly from the spacecraft pushed them gently over decades. In other words, the anomaly turned out to be a subtle engineering effect rather than a new law of nature. That result did not disappoint the field. It taught how easy it is to mistake an instrumental or engineering detail for a fundamental signal. And it showed the importance of building detailed models and of keeping an open mind until all mundane explanations are exhausted. A more recent and very prominent example of the fine line between false alarm and breakthrough comes from the study of a tiny particle called the muon. The muon behaves a lot like the electron, but with a heavier body and a faster life. Physicists can make muons wobble in a magnetic field and measure that wobble with extreme care. For many years, the measured wobble and the value predicted by theory did not match perfectly, and that gap grew into a headline story. In the last months, the experimental collaboration released its most precise measurement, and at the same time, theory groups have been refining the complex parts of the calculation that depend on the strong force. Some advanced computer-based methods, known as lattice quantum chromodynamics, have moved theory closer to the experimental number, while other approaches still leave tension. The muon story shows science at its best and most deliberate. Both experiment and theory sharpen themselves, and the community waits for consistency across several methods before calling anything definitive. Behind these stories lies a careful language of evidence and a set of rules for how to claim a discovery. In particle physics, a common standard has been the 5 sigma rule. That is a technical way to say that the odds of being fooled by random chance are extremely small. The 5 sigma convention is not holy law. It grew out of experience when many apparent anomalies dissolved under closer examination. The rule makes journals and the public comfortable that a claim is very unlikely to be a fluke. More generally, scientists use likelihood tests and other statistical tools that quantify how well a model fits data and how big the uncertainties are. Those methods help separate real signals from the many ways noise and bias can imitate a discovery. The math can be dense, but the idea is simple. If a pattern is strong enough and survives many checks, the community gains confidence that it reflects nature rather than chance. The peer review process and the wider culture of replication are the guardrails that keep the scientific conversation honest. When a team writes up a result, it goes to journals where outside experts read the work, probe its assumptions, and point out weaknesses. That criticism is not meant to block new ideas, but to strengthen them. When reviewers see shaky calibrations or unaccounted backgrounds, they ask for more tests or clearer explanations. Beyond peer review, a result becomes strong when independent teams using different devices and methods see the same effect. Reproducibility is the slow, steady friend of certainty. National and international efforts to encourage open data, clear methods, and shared code have grown precisely because the community recognizes how important independent checks are for separating real discoveries from mistakes. The way the media tells these stories can be both a help and a hindrance. Scientists often speak in cautious phrases that hedge what the data show and emphasize uncertainty. Journalists and headlines favor drama. The result can be a headline that implies certainty where there is only a careful hint. That tension matters because it shapes how the public sees science. Responsible communication means saying clearly what is known, what is not known, and why more checks are needed. It means celebrating careful null results as progress and explaining that ruling out ideas is a way of clearing the path toward the truth. The search for a new fundamental force feels like a long and gentle conversation with the universe. Scientists are not waiting for a lightning bolt to announce an answer. They are building better instruments, planning new runs, and learning how to listen more carefully. One of the clearest examples is the muon experiment that has kept the physics community on its toes. Teams at Fermilab have finished an extended program of measurements that sharpened the number everyone watches, and they and their peers are already planning how to squeeze still more precision from future runs and complementary facilities. Those next steps matter because a tiny change in their muon number would point to something beyond the three forces inside the standard particle model and gravity. At the same time, the big search is running on many fronts. Underground detectors are growing more sensitive and have pushed back the simplest ideas about what dark matter might be. New results from highly controlled liquid xenon experiments have not found the simple signals once expected, but their null results are themselves powerful because they tell theorists which paths are closed and where to look next. At the Particle Colliders, teams are upgrading accelerators and detectors to collect more collisions and to look for heavier or rarer carriers of force. Those planned improvements give the field both breadth and depth, letting small, precise experiments and large energetic machines probe complementary kinds of possibilities. Space will be an increasingly important lab. A small rock drifting around the sun carries a very clean record of forces that have acted on it for years. When a spacecraft like OSIRIS-REx visits an asteroid, it can measure tiny nudges caused by sunlight and by the rock warming and cooling. And those measurements let scientists test whether anything else is pushing. Some unexplained probes of the past have been traced to ordinary engineering effects, and that taught the community to be cautious. But modern missions with better instruments and longer tracking offer a new chance to use the emptiness of space to reveal subtle, long-range effects that a shy new force might show only outside the thick air and mass of Earth. At the same time, gravitational wave detectors are opening a new window on how gravity behaves under extreme conditions and are already being used to test ideas that change gravity at large scales. Together, these space and wave measurements widen the places where a new force could hide or reveal itself. A quiet revolution is also underway in the lab thanks to quantum technologies. Atomic clocks are now so precise that they can notice the tiniest shifts in energy levels. Spin-based quantum sensors and other atomic and optical tools can look for weak interactions that would have been invisible a decade ago. These devices work very differently from giant colliders. They do not smash things apart. They watch the stillness and read tiny differences in time or frequency or spin. Reviews by leading experts show that quantum sensing is becoming a major way to test ideas about new light particles and fields, and that many tabletop experiments can now probe ranges of mass and coupling that used to be the exclusive domain of large machines. This shift means that small teams with clever setups can make outsized contributions to the big questions. Artificial intelligence and modern machine learning are changing how experiments are run and how data are read. Computers help sift mountains of data to find the handful of events that might hide a surprise. Machine learning can also suggest patterns that humans might miss and point to new analysis paths that had not been tried. The physics community is careful, though. Teams work to make AI tools interpretable so that a machine's suggestion can be understood and checked by people. The growing literature shows that AI will not replace the hard work of experiment and theory, but will speed up the slow parts and uncover subtle signals that human eyes would not spot. What would success look like? Finding a new force would be a profound change in how we tell the story of the world. Textbooks would be rewritten, cosmology would be rethought, and new technologies might eventually follow from a deeper control of nature. But failure to find a new force is also valuable. Every careful null result narrows the possibilities and sharpens our questions. It forces better theories and better experiments. And in that steady narrowing, the path to truth becomes clearer. The search is, therefore, not a single dramatic event, but a long, patient craft, where negative answers are as honest and as useful as positive ones. The future of the hunt is therefore both technical and human. It depends on better magnets and cleaner sensors, but also on people learning to work across countries and disciplines, and to explain carefully what they find. It asks citizens to care about careful numbers and to celebrate the slow, patient folding of mistakes into understanding. If a fifth force waits in the wings, it will likely reveal itself as a stubborn, small discrepancy that survives many different tests. Until then, the next generation of experiments will keep listening, and the quiet, attentive work of many hands will be how we learn whether nature has one more secret to tell.